Where did the universe come from? What exactly was before the Big Bang? The most correct answer at present is, the universe comes from nothingness. So what is nothingness in the mouth of scientists? The content we are going to talk about today is relatively hardcore. After listening, it is estimated that your entire worldview will be refreshed. First of all, let's talk about the word nothingness. There is a correct definition. In the eyes of most people, nothingness is no light, no air, no sound. There are no examples either. It was quiet and dark at the same time. But here's a catch. In physics, this kind of nothingness is not allowed at all. Because in the eyes of physicists, even the most empty and lonely space, it has never really been quiet. Physicists call this state a vacuum state. Sounds quite tall. But in fact, it is said, space never stands still completely. In the world of quantum mechanics, vacuum, like a machine that never shuts down completely. There is always a tiny energy jumping around there. These energy fluctuations are known as vacuum fluctuations. They appear too quickly. It's so fast that we don't have time to measure directly. But their effects are real. There is an experiment that proves this. It's called the Casimir effect. If you hold metal plates very close, there will be a faint attraction between them. This force, it comes from those invisible quantum ups and downs. So you see, even the emptiest space we can create, in fact, it is not really empty. What's even more interesting is, physicists have also invented several different types of nothingness. For example, a false vacuum. He is like a stable-looking person. In fact, it is a state that can overturn at any time. It's like a ball stopping at the top of a mountain. It looks very stable, but with a gentle touch, will roll down. Some cosmologists believe this is how our universe may have begun. Then there's the desert space. It was Einstein, a solution to the general relativity equation. You can think of it as a sheet that is already taut, a blank canvas. Before you start painting, the cloth itself already carries energy. If the Big Bang started in desert space, the so-called nothingness, in fact, the materials for expansion have been prepared for a long time. If you look at it a little smaller, see Planck's scale. That's the minimum distance allowed by nature. The space may not be smooth at all. It will look like it's boiling. Countless tiny spacetime bubbles kept popping up. This state disappears again and is called a quantum bubble. It may be the most primitive nothingness we can describe. It is chaotic and unstable, unpredictable, but it may be the raw material for the birth of our universe. So you get the idea. When scientists say that the universe was born out of nothingness, they said, it's not what you and I imagined, the emptiness of nothing. They are talking about a vacuum full of ups and downs, or a false vacuum ready to decay at any time, or the desert space with its own energy, or quantum bubbles on the Planck scale. These states are active in their own ways. All leave the possibility for the birth of the universe. Speaking of which, we have to talk about the skyrocketing theory. To understand why someone is challenging him now, you have to know why he was so popular in the first place. The Big Bang theory itself can explain the universe. It swells out of a hot and dense state, but it left behind a few head-scratching puzzles. Early 1980s, Alan Guth and Andre Linde proposed the explosion theory. All these puzzles were solved at once. This is not a temporary patch. It's a big move to settle several troubles together. The first puzzle is called the world problem. In the cosmic background radiation, the residual heat left by those big explosions, the temperature in all directions in the sky is almost identical. But the problem is, according to the usual expansion rate, one end of the universe and the other. There is no opportunity to exchange information. How can we reach an agreement? The inflation theory says, because before it all starts, the entire universe was once small enough to communicate with each other. 大阻碍 balance can be achieved. The second is the flatness problem. Observations show our universe is geometrically shaped, very close to flat. But if there is no mechanism, the universe will either curl up quickly, or it will disperse too quickly. No structure can be formed. The explanation for the explosion is, he stretched the space too much. Any initial bands are smoothed out. It's like you are staring at a small piece of the surface of a balloon. No matter how round the ball is, it looks flat. The explosion also explains where the seeds of galaxies came from. In that crazy rapid expansion, tiny quantum ups and downs are stretched to the cosmic scale. These ups and downs later grew into mass of matter, formed galaxies, stars, and everything else. This is the quantum world and the cosmic world. Clever ways to connect. With so many advantages, the skyrocketing theory quickly became mainstream, but it's not perfect either. The biggest problem is, the surge depends on an unknown factory. It's called a surge of people, but no one ever found it. There are many different versions of the inflation theory. Each version of the forecast is slightly different. This makes it difficult to determine which one is right. For decades, explosion theory has always been dominant, because it matches the observations well. But these cracks, cosmologists have not stopped looking for alternatives. And this year, a new idea came out. Now 2025, one by Spain and Italy, a team of scientists. The leader is Raul from the University of Barcelona, Simenez. They asked the bold question, what if we don't need to report the bill at all? If gravity and quantum mechanics, these two things we have been familiar with for a long time, that alone is enough to explain the origin of the universe. Here's what they think. Remember what we just said about the desert space. The team builds on this. Add some gravitational waves. And these gravitational waves, no black holes or supernova are needed to make it. They are simply natural properties of spacetime itself. In their vision, the early universe may have started from the beginning. It is full of these ripples of time and space. These ripples superimpose each other. It may be enough to shape the original structure. The researchers did the math, discovered that these waves are not just passive dangling, then disappear. They influence each other. These interactions accumulate and leave traces. Subtle changes in energy in space. Over time, these small changes, it is exactly what is needed for the formation of the structure. Galaxy clusters. And also, all the large cosmic structures we see today. If the idea is correct, the early universe didn't need an explosion field at all. The ripples of time and space are enough. This is the core point. And the interesting part is, he did not introduce anything new and untested. Gravitational waves are real. We have detected it on Earth. General relativity that predicts gravitational waves withstands all the tests for over 100 years. And quantum mechanics that ensures long-term existence. It is the most reliable theoretical framework we have. This new model tries to show these two pillars are combined, can do the job of shaping the early universe. No speculative additions are required. Of course, this does not mean that the debate is over. Mathematics must match observations. In particular, cosmic microwave background radiation. This is the gold standard for examining any early model of the universe. The theory of inflation has made achievements in this regard. It explains why background radiation is so smooth overall, but there are small changes that we observe. The gravitational wave model must meet the same standard. But even in the early stages, this proposal is also important because it changes the direction of the conversation. Long reporting is the only serious option. Now here's a concrete alternative, and he doesn't rely on hidden physics. He said that the universe may be based on the ripples of time and space. Do what they would naturally do and it kicks in. It's not that mysterious. So how do we know if this idea is right? The answer is that it depends on the evidence. Any new ideas about the early universe, it all has to be on paper. It sounds reliable. We also have to leave fingerprints that we can actually observe. This is the only thing that can be known. Does he have a chance to counter the inflation theory? Despite the skyrocketing problems. But he does have the same thing as what we see in the sky. It's quite a coincidence. For the gravitational wave model, the main test is, can he recreate the cosmic microwave background? Small changes in radiation. The faint light left by the Big Bang. The explosion theory says, these changes come from the stretched quantum fluctuations. The new model says, gravitational waves can do the same thing. If this is true, statistical patterns in microwave backgrounds, it should take on a certain look. Cosmologists have been able to do so with amazing precision, measure these patterns. So contrast is inevitable. Another big clue will come from the gravitational wave itself. Surge theory prediction. There is an extremely weak primordial. The gravitational wave background is so weak that we haven't caught it yet. The new model also predicts this signal. If we can do this by studying the polarization of the microwave background of the universe, or through a specially designed design, instruments to capture low-frequency gravitational waves, detected him, can support or exclude this idea. There is also the way structures are distributed in the universe. Galaxies and galaxy clusters, distribution patterns at the largest scale. These patterns come from seeds planted in the early universe. Explosions leave very specific marks. If gravitational waves are really the source, the details of this imprint may vary. Upcoming galaxy surveys, it will help us paint this picture more clearly. Simply put, the evidence must be microwaved in 3 places. Gravitational wave background. There is also the large-scale structure of the universe. If this new model can be without the need for explosives, meet these standards, then he is eligible to compete. If you can't, the inflation theory temporarily maintains its position. It is not easy to actually measure these things. The early universe is gone, but the signal he left behind is still there, just faintly, buried in the noise, often overwhelmed by more recent events in the universe. But that didn't stop it. Scientists built instruments with ridiculously high sensitivity just to find them. The cosmic microwave background is the first. It is also the most important observation target. We have already used it to test the explosion theory. It's the same now. Microwave backgrounds are more than just a layer of light. It is a detailed map. The temperature varies slightly from location to location. These differences tell us what happened in the first hundreds of thousands of years after the Big Bang. But the microwave background has a more useful characteristic: polarization. When light scatters, it becomes polarized. The light in the microwave background carries this information. The surge theory predicts polarization. There will be a faint vortex pattern in the middle. It's called mode B. These B patterns are detected. It is one of the holy grails of cosmology, because they would be direct evidence of the original gravitational waves. The trouble is that the signal is too small. It's easy to get along with us in the galaxy. Dust from foreground noise is confusing. That's why experiments like LIGHTBIRD Launch is planned in the early 2030s. It is designed to be extremely sensitive. It is to single out these patterns. If LightBird or other microwave background experiments successfully measured them, we have clear goals to test the new model. Microwave backgrounds are not the only window. The gravitational wave itself spans a wide range of frequencies. Different detectors are tuned to different frequency bands. Observatories like LIGO and Virgo already listening. High-frequency events produced by the merger of black holes and neutron stars. But for the early universe, we need to go much lower. This is the pulsar, where timing arrays come in handy. Pulsars are like lighthouses, stars that emit regular radio signals. By observing the ticking sound of pulsar regularity, astronomers can find ultra-long waves, small disturbances caused by long gravitational waves. In 2023, these cracks detected signs of background signals. Most of it may come from collisions of supermassive black holes. But the possibility of the original ingredient has not been ruled out. If that background is proven in the end, contains early cosmic signals, that would be a huge step forward. And then there is LISA, Space Gravitational Wave Detector. It is also planned to launch in the 2030s. Unlike ground detectors, LISA will stay in space, measure satellites millions of kilometers apart, distance between. This makes him very interested in us on Earth. Unreachable frequency range sensitive. If the original gravitational wave is in that frequency band, LISA can see them. Gravitational wave model for 2025. It needs to be consistent with LISA's findings, or explain why it is inconsistent. At last, large-scale galactic surveys are adding another layer of evidence. By mapping millions of galaxies, trace how matter is distributed on a cosmic scale. They let us see directly how the structure of the universe has evolved over time. Inflation theory is documented in matching these structures. New models need to compete. It has to be without relying on the inflator. Produces the same large-scale distribution. Upcoming WILA. Observations by telescopes such as the Rubin Observatory. It will make this contrast clearer. So you see, evidence is not hidden in one place. It is scattered in the microwave background all over the sky. The timing of the pulsar. Each observation gives us a piece of the puzzle. If they both point in the same direction, we know the gravitational wave origin model is an interesting paper. It is still a real subsistence for the inflation theory. Speaking of which, we have to talk about quantum mechanics. If you seriously ask how the universe began, there's no way around it. Quantum mechanics tells us, when we narrow down to the smallest possible scale, what happens? And the early universe was not just small. It has been pushed to the limit where quantum rules rule everything. The most important point is the uncertainty principle. At the tiniest scale, nothing stands still. Energy and constant ups and downs. This is true even at the lowest possible energy state. This means, if we imagine the beginning of the universe, it will not be completely smooth or completely calm. It will be jittery in nature, because quantum mechanics does not allow perfect stillness. These jitters are not just noise. They were later stretched and amplified into galaxies, raw materials for stars and planets. Now when people hear that the universe comes from quantum ups and downs, it may sound like fooling people, like a rabbit coming out of a hat. But the point is more subtle. Quantum theory does not say, the universe just came out of nowhere. What he said was, when you put the rules of the quantum field, when applied to spacetime itself, ups and downs are inevitable. If time and space can ripple, as the gravitational wave model suggests, then quantum mechanics guarantees these ripples are never perfectly even. They carry small changes, and it was these changes that played a role later. There is also a concept called retreat coherence. In the quantum world, systems can exist in overlapping states at the same time. It's like being in two situations at the same time. But in a big, chaotic environment, these overlaps collapse into a single classical result. In the early universe, the retreat may be, put those fragile quantum ripples, the process of becoming a stable density and structural pattern. These patterns can continue and grow. There is no retreat. Faults stay in strange superpositions, real but not locked into the deterministic pattern we actually observe. Some researchers also talk about the idea of quantum bubbles. On the Planck scale, space-time itself is boiling and unstable. If this picture is true, then what we call the birth of the universe, probably just a small piece of this bubble, become big enough and stable enough, so much so that it can swell at the moment. Carry quantum rules with you. From this perspective, the Big Bang is not a single creation at a time. It's a transformation. Jump from microscopic chaos to macroscopic order. Here's why. Quantum mechanics is crucial to this debate. It is not just an add-on to cosmology. He defined the universe in the first moment, a stage that must be performed. Whether the story involves explosions or quotations, force wave quantum rules, all provide the growth of the structure. Without them, you will end up with a perfectly smooth universe. And a perfect and smooth universe cannot create a stellar galaxy, not to mention humans. The challenge lies in quantum mechanics and general relativity, two theories we rely on. It doesn't get along well when pushed to extremes. The theory of relativity works very well on large scales. Quantum theory works well on small scales. But when we try to force them together, for example, in the first moments of the universe, they will clash. Here's why. Some physicists explore the quantum gravitational sphere, quantum cosmology, or string theory. These are all attempts to find one. It can handle both frameworks at the same time. Try. The interesting thing about the gravitational wave proposal in 2025 is that it tries to show maybe you don't need a complete theory of quantum gravity to explain the earliest moments. You may just need to take it seriously. Quantum ripples of spacetime. So the role of quantum mechanics is not optional. It is the skeleton. He made sure that the vacuum was not really empty. He provides protection against perfectly uniform jitter. He may even explain how the early universe was frozen in the pattern we are observing now. Without quantum rules, there is no seed of structure. There are no seeds. The universe would be inanimate and featureless. People always wonder what preceded the Big Bang. The problem is the word before. It only makes sense when time is already running. If time itself began with the Big Bang, then it doesn't hold true if you ask what it was before. Someone made an analogy. It's like asking what is north of the North Pole. But that didn't stop it. Scientists try to give some meaning to this question. One way is to bounce back the idea. It's not so much a real beginning. The universe may go through endless cycles of collapse and expansion. In that case, our Big Bang is just the latest rally. Nobel laureate Roger, another idea from Penrose. Think of a universe in the distant future. It can smoothly transform into the birth of the next one. This is another way of saying that there was something before, even if it looks unlike the time circle we usually understand. Quantum cosmology offers another angle. In that frame, quantum effects prevent the universe from reaching its true starting point. Not everything is compressed to a point. The space reaches the minimum possible size, then bounces outward. This made the Big Bang a sharp start. replaced by a transformation, gravitational wave. The proposal was not elaborated in the same way. What he suggested, we call it the state of beginning. It may be more like a transformation. Instead of creating suddenly, if spacetime starts from the beginning, it is full of built-in ripples. So, the Big Bang is not a spark bursting out of nothingness. It is a change in the way these ripples evolve. So maybe the real answer is, the universe simply does not have an absolute beginning. Maybe it starts with a cycle of bounces one at a time, or a state change. Or perhaps time itself began with the Big Bang. The previous term did not apply at all. Here, you must understand it all. Nothingness is not what most people think. It's not a blank slate, not a dark void. Nor is it some kind of absolute. The void suddenly gave way to the universe. In physics, nothingness is always a vacuum in which something is full of energy, geometric structures capable of stretching and bending, or a background full of ripples that refuse to stand still. This is the new idea about the universe. Why it's so compelling? The inflation theory tells we need an additional component to explode the magnetic field, to make things work. That was the price of solving the puzzles of the early universe. But the gravitational wave model stripped that away, saying that maybe the baseline itself is enough. Perhaps spacetime was restless from the beginning. Being full of quantum nature can create seeds, the inhomogeneity of everything we see today. This is a big shift in the way we think about origins. Instead of asking what created the universe out of nothingness, it is better to ask what kind of nothingness it is. It is a smooth expansion. Is it a desert space that locks energy inside? Is it a quantum bubble full of ups and downs? Or is it an unstable vacuum on the verge of transformation? Each answer is different, but they all show what the word nothingness hides, far stronger than him. The beauty of this debate is that it is not just abstract speculation. These thoughts leave measurable traces. The way galaxies are distributed, a faint polarization pattern in the cosmic microwave background, the hum that the primordial gravitational wave may emit. All of this is testable. If the evidence matches the fingerprints predicted by spatiotemporal ripples, then the old picture of nothingness giving way to the account. It may be replaced by something more streamlined, with physics that we already know. What was before the Big Bang was built? There may never be a final answer to the question. Maybe there was a rebound. Maybe there is a loop. Or maybe time itself began at that moment. The previous term did not apply, but it is becoming clearer. The beginning is not absolute emptiness. It is a state of structure, regularity, and energy, enough to produce one, can evolve into the universe we see now. This changes how we think about ourselves, the way of being placed in this story. We don't live in one, from the universe born of the perfect void. We is a rule that may always be in its most basic rules, a piece of the universe that carries the potential for growth. The universe does not come from nothing. It comes from something that we are only beginning to understand, a certain existence of restlessness,